Let's talk about how to find the domain of a function. Here's the basic idea. A function is a little machine. You feed it an x value and it hands you back an output. The domain is simply the list of every x value you're allowed to feed into that machine without it breaking down. Some x values are perfectly safe. Others cause problems like dividing by 0 or taking the square root of a negative number, and we have to exclude those. In this video, we'll go through it slowly, one type of function at a time. First, polynomials, which are always safe, then rational functions where a fraction can break, and finally radical functions where a square root can break. By the end, you'll have a simple checklist you can use on any function you see. Let's start with the easiest case. Polynomial functions. A polynomial is just x's being added, subtracted, multiplied, and raised to whole number powers. No x underneath a fraction, and no x underneath a square root. Since there's no fraction, there's no risk of dividing by 0. And since there's no square root, there's no risk of a negative number causing trouble. That means there is nothing in a polynomial that can ever break. So here's the rule. For any polynomial, the domain is always every real number. Let's take our first example. F of x equals 2x minus 7. This is a linear function. Its graph is just a straight line. Pick literally any number you like for x. 0, 100, negative 50, even a fraction like 1/2. Multiply it by 2, subtract 7, and you always get a real number back. Nothing ever goes wrong, so the domain is all real numbers, which in interval notation we write as negative infinity to positive infinity. Now a quadratic, f of x equals x squared plus 3x minus 5. This one has an x squared term, but that's still totally safe. Squaring a number, whether it's positive or negative, always gives you a real number. Then we're just adding, multiplying, and subtracting. None of those operations can ever break. So just like before, the domain is still all real numbers, negative infinity to positive infinity. And it doesn't matter how high the degree of the polynomial gets. Look at this cubic, 2x cubed minus 5x squared plus 7x minus 3. You could raise x to the 10th power, the 100th power, as long as there's still no fraction and no square root anywhere. None of that changes anything. There's still nothing to break. The domain is, once again, all real numbers. Now let's move to a category where things actually can go wrong. Rational functions. A rational function is any function where x shows up in the denominator of a fraction on the bottom. And here's the one rule you need to remember. In math, dividing by 0 is undefined. It's not that it equals some huge number or a strange number. The operation simply doesn't produce an answer at all. So whenever we see a fraction, our first move is always the same. Take the denominator, set it not equal to 0, and solve for x. Whatever x value you find gets kicked out of the domain. Let's try it. F of x equals 5 divided by x minus 2. Ask yourself, what value of x makes the bottom? X minus 2 equal to 0. Set up the equation. X minus 2 not equal to 0. Add 2 to both sides and you get x not equal to 2. Let's double check that makes sense. If you plugged in x equals 2, the denominator would become 2 minus 2, which is 0, and 5 divided by 0 is undefined. So x equals 2 is the one value we have to remove. Every other real number is perfectly fine. The domain is all real numbers except 2, which we write as negative infinity to 2, union 2 to positive infinity. This next one has a trinomial on the bottom. F of x equals 3x minus 8 divided by x squared minus 9x plus 20. A trinomial is just a three-term expression like this, and to find where it equals 0, the easiest approach is to factor it. We need two numbers that multiply together to give positive 20, but add together to give negative 9. If you think it through, negative 4 and negative 5 do the job. Negative 4 times negative 5 is 20, and negative 4 plus negative 5 is negative 9. So the denominator factors into x minus 4 times x minus 5. For the whole product to be 0, one of those two factors has to be 0. So either x minus 4 equals 0, giving x equals 4, or x minus 5 equals 0, giving x equals 5. Both of those values have to be excluded. The domain is all real numbers except 4 and 5. Here's a trickier looking one. F of x equals 2x minus 3 divided by x squared plus 4. As always, we set the denominator not equal to 0. X squared plus 4 not equal to 0. Subtract 4 from both sides, and you get x squared not equal to negative 4. Now think carefully about what squaring actually does. If you square a positive number, you get a positive result. If you square a negative number, the two negative signs cancel and you still get a positive result. So squaring any real number can never ever produce a negative answer. That means x squared equals negative 4 is simply impossible. There is no real x value that breaks this denominator. So, surprisingly, the domain here is all real numbers, even though it's a fraction. Our last category is radical functions, functions with a square root. Here's the key fact you need. A square root asks the question, what number times itself gives me this value underneath? Since squaring any real number always gives a non-negative result, there is no real number whose square root is negative. In other words, you can never take the square root of a negative number and get a real answer. So the rule is, whatever is underneath the square root sign must be 0 or greater. There's one small twist. If that square root happens to be sitting in a denominator, it can't equal 0 either, because we still can't divide by 0. So in a denominator, the inside must be strictly greater than 0, not just 0 or greater. Let's apply that. F of x equals the square root of x minus 4. The inside of the square root, x minus 4, has to be greater than or equal to 0. Add 4 to both sides and you get x is greater than or equal to 4. Notice we can include 4 itself here since the square root of 0 is simply 0. That's a perfectly valid defined answer. So the domain is 4 up to positive infinity, and because 4 is included, we use a square bracket on that side, 4, infinity. This example needs factoring before we can even test it. The square root of x squared plus 3x minus 28. Set the inside greater than or equal to 0, then factor x squared plus 3x minus 28. We need two numbers multiplying to negative 28 and adding to positive 3, that's positive 7 and negative 4. So it factors into x minus 4 times x plus 7 greater than or equal to 0. Those two boundary points, negative 7 and 4, split the number line into 3 regions, and because we're multiplying two factors together, we need to test each region to see if the product is positive or negative. Try x equals negative 8, which is left of both boundaries. You get a negative times a negative, which is positive. That region works. Try x equals 0 in the middle, negative times positive, which is negative, that region fails, since we can't have a negative under a square root. Try x equals 5 to the right of both boundaries. Positive times positive, which is positive again, that region works too. So we keep the two outer regions and throw away the middle. The domain is x less than or equal to negative 7, or x greater than or equal to 4. Now watch what happens when the square root moves into the denominator. F of x equals 1, divided by the square root of x plus 3. We still need the inside to be non-negative, but remember the extra rule, since this square root is on the bottom of a fraction, it can't equal 0 either, or we'd be dividing by 0. So instead of greater than or equal to 0, we need x plus 3 strictly greater than 0. Subtract 3 from both sides. X is strictly greater than negative 3. Because negative 3 itself is excluded this time, we use a round parenthesis instead of a bracket. The domain is negative 3, infinity, with negative 3 not included. Now let's combine ideas. F of x equals the square root of x minus 4, all divided by x squared minus 25. There are two separate conditions here, so we check the numerator and the denominator, one at a time. For the square root on top, x minus 4 must be greater than or equal to 0, which gives x greater than or equal to 4. For the denominator, x squared minus 25 cannot equal 0. That's a difference of squares, so it factors into x plus 5 times x minus 5, which means x cannot be negative 5 and x cannot be 5. Now here's the important part. Since we already require x to be at least 4, the restriction against negative 5 is irrelevant because negative 5 was never going to be in our domain anyway. Only the restriction against 5 still matters, so the domain starts at 4, includes 4, runs all the way to infinity, but has to skip over the single broken point at 5, 4, 5, with a bracket on the 4 and a parenthesis on the 5, union 5 to infinity. This is the trickiest case of all. a square root on the top and a square root on the bottom. F of x equals the square root of x plus 3, all divided by the square root of x squared minus 16. Since there are two separate radicals, we have to solve two separate conditions and then find where they overlap, where both are true at the same time. First, the numerator. X plus 3 must be greater than or equal to 0, which gives x greater than or equal to negative 3. Second, the denominator. Since it's a square root in the bottom of a fraction, x squared minus 16 must be strictly greater than 0. Factor it as x plus 4 times x minus 4, and sign test it just like before. This product is positive when x is less than negative 4 or when x is greater than 4. Now we line up both conditions on the same number line, and look for where they agree to the left of negative 3. The numerator condition already fails, so that's out. Between negative 3 and 4, the numerator is fine, but the denominator condition fails there, so that's out too. The only place left where both conditions hold at once is past x equals 4. And notice that x equals 4 itself still makes the denominator's square root equal to 0, which is still not allowed in a denominator, so 4 stays excluded. The final domain is everything strictly greater than 4. Let's recap everything with one simple checklist you can use on any function. First, look for a fraction or a square root if you see neither. It's a plain polynomial. The domain is always all real numbers, nothing to check. If you see a fraction, take the denominator, set it not equal to 0. Solve and exclude whatever x values you find, because dividing by 0 is never allowed. If you see a square root sitting alone or in a numerator, set the inside greater than or equal to 0, since you can never take the square root of a negative number. If that square root is sitting in a denominator, use strictly greater than 0 instead, since it still can't equal 0. And if you ever have square roots on both the top and the bottom, solve each condition on its own, then keep only the x values where both conditions are true at the same time. Work through those checks in order, one at a time, and you can find the domain of absolutely any function.